In this video, we're going to look at the rules of exponents for integer exponents. That'll include positive numbers, 0, and negative numbers. First, we have the product of powers. In this case, when we multiply two things with the same base, we combine them by adding the exponents. We can check this with a simple example. X squared times x cubed is x squared times x cubed, and you can see we end up with 5 x's altogether, or x to the fifth. Our next rule is for a power of a power, and in this case we multiply the exponents. Let's check this with an example. X squared to the third power is x squared times x squared times x squared, and you can see that we now have 6 x's in the product. It's easy to mix these two rules up, so I recommend using these two examples to help keep them straight. And our last rule for products is the power of a product. In this case, we can apply the exponent to both of the factors inside the parentheses, as long as this is multiplication. Let's check this one. 2x to the third power. We'll write that out the long way. 2x times 2x times 2x. And you can see we have 2 to the third power and x to the third power. And that simplifies to 8x cubed. Of course, you wouldn't write these out the long way when you apply the rules. We're just doing that to demonstrate why the rules work. Our next rule is going to involve quotients, and it's going to be similar to this rule involving products. When we multiply the two factors, we add the exponents, and we'll see when we divide them, we will subtract. So here's the rule for a quotient of powers, which tells us to subtract the exponents. Notice the way it's written here, we're subtracting the bottom exponent from the top exponent. Let's try this with an example. Y to the fifth over y to the third. Applying the quotient rule, we subtract the 3 from the 5, and we're left with y squared. Let's write this out the long way so we can see why it works. We put y to the fifth in the top and y to the third in the bottom, and then we cancel common factors, and we can see we're left with y squared. Notice in this example, we are subtracting the bottom exponent from the top exponent, which makes sense because the top exponent is larger. But what would happen if we had a larger exponent in the denominator? Here's an example like that. We have the larger exponent in the denominator. Let's write this out the long way first. W squared over w to the sixth power. Cancel the common factors, and we should be left with 1 over w to the fourth power. This tells us that we should also be able to subtract the top exponent from the bottom exponent, and that will be the case. We will have two different ways that we can state the quotient rule. So here they are. Here's the first version, where we subtract with the top exponent first and put the result in the numerator. The alternative version is to subtract with the bottom exponent first and put the result in the denominator. Now, normally you will use one version or the other depending on whether the top or the bottom has the larger exponent. But a good question is, will both forms work on the same example? Let's try it. Previously, we had w to the second power over w to the sixth power. And in this case, it's natural to subtract the top exponent from the bottom because the bottom is larger, and we end up with 1 over w to the fourth. If we apply the other version of the rule, and we subtract with the top exponent first, and leave the result in the numerator, we end up with a negative exponent, w to the negative fourth power. And if this rule is going to be consistent, or if these rules are going to be consistent, we need these two expressions to be equal to each other. In other words, w to the negative fourth power has to equal 1 over w to the fourth power. And that gives us a rule for negative exponents. A to the negative n is equal to 1 over a to the n. Negative exponents will mean reciprocals. Here's an example. 5 to the negative 2 power is 1 over 5 squared. You change the negative exponent to a positive exponent when you move the factor from top to bottom. A common mistake is to assume that the negative exponent makes the expression negative. 5 to the negative 2 is not negative 5 squared. It is 1 over 5 squared. There's one last case we want to look at involving quotients, and that's when the top and the bottom have the same exponent. In this case, we could just cancel these as single factors, or we could write it out the long way and cancel all the factors individually. But either way, when all the factors cancel, we end up with 1. Now, if we apply the quotient rule, we will subtract the exponents, and that'll leave us with x to the 0 power. And again, for the quotient rule to be consistent, these two expressions need to be equal. So x to the 0 power needs to equal 1. And that's going to give us a rule for 0 exponents. A base raised to the 0 power is equal to 1. Now you can see from the argument above that it doesn't matter what the base is equal to. Since all the factors cancel out, we're just left with 1. So this works for any base with one exception. We don't allow our bases to equal 0. 0 to the 0 power is something we can investigate further in a calculus course, but for now we'll just consider it to be undefined. 0 to the 0 power does not have a value. So let's summarize the quotient rules that we've had. First, we had the quotient of powers. If we subtracted with the top exponent first, we put the result in the numerator. If we subtracted with the bottom exponent first, we put the result in the denominator. Then we had a rule for negative exponents. We took the reciprocal of something to a negative power by moving it to the denominator and changing the exponent from negative to positive. We could also have a factor with a negative exponent in the denominator and take its reciprocal by moving it to the numerator and changing the exponent from negative to positive. So factors can be moved from top to bottom or bottom to top if we change the sign, the plus or minus, on the exponent. There's actually a third way we could state this rule. If we have a fraction raised to a negative power, we could apply both of these at once by taking the reciprocal of the fraction and changing the exponent from negative to positive. Then we had the rule for 0 exponents. Anything to the 0 power is equal to 1 as long as the base is not equal to 0. And finally, there's one last rule for quotients. When we have a fraction or a quotient raised to a power, we can apply that exponent separately to the top and the bottom, just like we did for products. And we can check this easily. X over y to the third power, for example, can be written out the long way, and we see that we multiply 3 x's in the numerator and 3 y's in the denominator. Let's look at all the rules we just covered. First, we looked at the power of a power, where we multiply the exponents, and then a product of powers, where we add the exponents. Similarly, we had a quotient of powers, where we subtract the exponents, either in the top or the bottom. We also had a power of products, where we apply the exponent to each factor separately. And similar to that, there was a power of quotients, where we apply the exponent to the top and the bottom separately. We had a rule for negative exponents, which meant reciprocals. We move factors from top to bottom or bottom to top when we change the sign of the exponent. And a 0 exponent rule, which says anything to the 0 power is equal to 1 as long as the base is not equal to 0. And notice here that all of these rules involve products and quotients. None of them involve addition or subtraction. For example, a plus b to the second power does not equal a squared plus b squared. It's a very common mistake. Remember, you would have to multiply a plus b times a plus b and distribute, and you would get a squared plus 2ab plus b squared. So you'd be missing this middle term if you try to distribute this exponent to the inside. You can only apply the exponent to the inside of the parentheses if you have multiplication or division. Another common mistake when combining like terms is to think that you change the exponent. Remember, when you combine like terms, you simply add the coefficients and you leave the exponent the same. And if the exponents were different, then you wouldn't be able to combine the terms anyway.